This next chapter is chapter 7, which is on linear momentum. And so momentum is given to be the mass times the velocity. So m is again is the mass, which will be in kilograms. V is the velocity of the object, which will be in meters per second. And P, with lowercase p, is the momentum, which will be in terms of a kilogram meter per second. So we have in terms of momentum. So if you think about momentum and you compare the momentum, you think of that of a bullet being fired from a gun compared to the momentum of one of the trains that go out here on the tracks behind the building. And you say, well, which one would have a greater momentum? Well, that the bullet has a higher velocity, but its mass would be quite small compared to that of the trains out here, which in terms of velocity, not very fast, but in terms of mass, they are far more massive and would have a greater momentum. Okay. So force is given to be the change in the momentum over the change in the time. And the change in momentum then, here, you got that change in momentum will be given by the mass times the change in velocity, given that the mass of the object is not going to change, but its velocity would. And so we get that the force would equal m delta v over delta t. But then again, you go back to those equations from chapter 2, and we said that acceleration was the change in velocity over the change in time. And so we get that F equals ma, which again was Newton's second law of motion. Right? Well, in terms of momentum then, we look in terms of conservation of momentum. So whatever you start with is what you end up with. So the momentum before has to equal the momentum after. And so an example of that would then be the following problem. So if you think about two people, maybe an adult and a child, on the middle of a skating rink. And then they push off of each other. And so the parent goes in one direction, the child goes in the other direction. So you do this. So a 100 kilogram adult and a 30 kilogram child on an ice rink. Push off of each other. If the child has a velocity of 4 meters per second, what is the velocity of the adult? So, and what you have the adult, you have the kid, they push off of each other, so the kid goes this way, the adult goes that way. We said that the child has a velocity of 4 meters per second, so we get the mass of the adult is 100 kilograms. we get the mass of the child is 30 kilograms. The velocity of the adult is what we're trying to find, and the velocity of the child we have, which was 4 meters per second. Given that there is conservation momentum, we know the momentum before has to equal the momentum after. And so we have that the mass of the adult times the velocity of the adult will have to equal the mass of the child times the velocity of the child. Okay. And in this case, we want to find the velocity of the adult, so we can divide by the mass. And so the velocity of the adult will be given by the mass of the child times the velocity of the child divided by the mass of the adult. So we take our numbers and we plug them in. We end up that the velocity of the adult is going to equal 30 times 4 divided by 100, and my adult would be moving with a rate of 1.2 meters per second. Yeah. Which means that in 10 seconds, my adult would have covered a distance of 12 meters. So we have in terms of conservation of momentum. Well, the other thing to look at here is in terms of impulse. So you have the impulse so we have that force was given by the change in momentum over the change in time. And the change in momentum would then be F times delta T. And this is impulse. So impulse then is basically the change in momentum. And so you have in terms of, you think about a car crash and all those forces and the time frame, is you want to minimize the impulse to the passengers in the car. Right? So in terms of collisions, there are 2 types of collisions the chapter talks about. So there are 2 types of collisions. And those types are elastic, and then the other type is inelastic. Elastic collisions, you think in terms of if you're shooting pool. Right? That you strike the cue ball, it hits whatever ball you're aiming at, that ball takes off at the velocity, the cue ball stops. Right? So in elastic collisions, you have conservation of momentum, and you also have conservation of kinetic energy. So both things are conserved in an elastic collision. An inelastic collision is basically any day on I-5, and you have the various car crashes that occur. So you have first, in terms of momentum, there is conservation of momentum. But there is a loss of kinetic energy. So the kinetic energy before will be greater than the kinetic energy after. And partly due to this fact that there is conservation of momentum, you can actually look in terms of a wreck and figure out what happened. And so really you think in terms of the state patrol when they go out and they investigate, felony car crashes. They have to look at these sort of things. So first off, what happens in terms of this type of a collision? Elastic collision. And we're going to just look in terms of the case when we have our first object, which is moving at a velocity. So this is m1, and it's moving at some velocity v0. And then it's going to strike our subject, the second object, m2, which is at rest. So it has no initial velocity. And we want to look what's going to happen in terms of the various scenarios here. So there's a couple equations that will relate our velocities. Right? And so you get that v1 final will be given by m1 minus m2 over m1 plus m2 times v0. Right? And then v2 final will be given by twice m1 over m1 plus m2 times v0. These two equations, they go through to how they got those in the book, but basically we got those by a simultaneous equation involving both momentum and kinetic energy, and you get to that point. Right? So in terms of those two equations, let's look at three different possible scenarios. Right? And so the first one would be if m1 is equal to m2. So you think again like if when you're playing pool. You strike the cue ball, it moves with a velocity. It hits whatever ball you're aiming at dead on, and you know that that ball takes off and the cue ball will come to a stop. So if m1 equals m2, well then this ends up being 0, and you get that v1 final is going to be equal to 0. Right? And then if we come over here, we got v2 final. Well, given m1 equals m2, we got that this fraction will be 1, and so v2 final will equal v0. And again, you know that when you play pool. Okay. Next scenario. Now we have this. So now if m1 is much, much greater than m2, right? So you think about these two objects both having the same diameter, but let's say that now m1 is on the order of 1,000 kilograms and m2 is on the order of 1 kilogram. Well, what happened? Well, if you think about it, this one is much more massive, and so eventually it's just going to come through here, and it's just going to keep on going. M2 will have basically no impact on it. And then you have, once that it hits M2, well, M2 is going to just take off in that direction. Right? Right? So what happens here? Well, V1 final. Well, if M1 is much, much greater than M2, then basically you think about my scenario where I said 1,001. Well, you get 1,000 minus 1 is 999. You get 1,000 plus 1 would be 1,001. 999 divided by 1,001 is basically 1. And so you have that basically the velocity of my first object doesn't change. Okay. Now V2 final. Well, again, M2 contributes really nothing. So you get 2m1 over m1, and that'll be 2. And so this object will take off with twice the velocity. And then the third scenario is now we change what happens, and now we have that M1 is much, much less than M2. So now this is the light object. It comes in, it hits this object, which is much more massive than the one we have. And so basically what's going to happen is it's going to hit, and then it is going to bounce back. And this one basically is not going to move. So we have V1 final. Right. So then we got M1 basically contributes nothing. So you get negative M2 over a positive M2, which will be a negative 1. So you get negative V0. And then you get V2 final. You get a very small number divided by a very large number. And you get that this will basically be 0. So that object is not going to go anywhere. Right? So we have what happens in terms of the elastic collision and those three different scenarios. Right? Well, now what happens in terms of an inelastic collision, and we'll go to a common scenario, and that is what happens in the case of a car crash at an intersection. So now we have in terms of an inelastic collision. And again, my scenario is going to be is I have these cars at an intersection, and we want to see what happens. So here's my first vehicle. M1 is 1,000 kilograms, and the velocity is 20 meters per second. Okay? And then we have my second vehicle over here, and M2 is 2,000 kilograms, and V2 is 20 meters per second. And we get, they both come up to this intersection, neither one stops at the stop sign, and they meet here. And the question then is, well, what happens to the wreckage, right? So basically you got that they meet here, we get the my blue vehicle, we get this vehicle, which is going to merge into it, and it's going to take off in that direction. So I'm going to know now what happens in terms of that initial stages of this wreck. So I want to know what is the velocity that the wreckage moves off at, and at what angle. So we want to find it, what is the initial velocity after collision, and we want to know at what angle this goes off at. Right? So we want to find those two things in regards to our problem. Right? Right? So, when I do this, we're going to look in terms of the various components here. So if I look at vehicle 1, this one is only traveling in the x direction. Right? And so we're going to look in terms of its momentum. So for vehicle 1, its momentum is only in the x direction, and so it'll be 1,000 times my 20. And so we get 20,000 kilograms meters per second. And then in the y direction, this momentum is 0. Okay? For vehicle number 2, it's only moving in the y direction, so its momentum in the x direction will be 0, and its momentum in the y direction will be given by mass times velocity, and so that'll come out to be 40,000 that. So we know the x and y component of the momentum before, which means that the x and y component before has to be equal to the x and y component after. And so after collision, we would have that this is what happens to the wreckage. It's going to go off with 20,000 this way, and then it'll be 40,000 this way, and what we're going to want will then be the hypotenuse of this right triangle. And so that is Pythagorean theorem. And so the momentum after collision, the momentum after collision is going to be the square root of 20,000 squared plus 40,000 squared. And we plug that in, and that comes out to be 44,721 kilograms meters per second. So that's momentum, but I want to know the velocity. Well, momentum, we said, was mass times velocity, which means velocity is the momentum divided by the mass. So here we get 44,721. Now the mass here is going to be the combined mass of these two as they moved off. And so that's going to be 3,000. And so we find out that initially the wreckage moves off at 14.9 meters per second. Well, the next part then is, well, what angle do they take off at? And so I want to know this angle here, theta. And so we have that this is the opposite side, this is the adjacent side. And so we get that tan theta is going to be given by the momentum in the y divided by the momentum in the x. And so theta is going to be the inverse tangent of those two. And so we have here that theta will be the inverse tangent of 40,000 over 20,000. And this comes out to be 63.4 degrees. So we know that in terms of the initial stages of this accident, that when they meet, this is going to move off with a rate of 14.9 meters per second at an angle of 63.4 degrees. And based on these types of calculations is what the State Patrol does. When they go to investigate felony wrecks, they get these measurements, and then they can do these types of calculations and figure out what were the various speeds of the cars involved. Now, another example of an inelastic collision, and one that we'll be doing in terms of a lab, is what happens in terms of a ballistic pendulum. So in terms of a ballistic pendulum, what happens? So we have, basically, we have a block which is suspended, which will have some mass, we'll call it big M. And then we're going to fire a bullet, a projectile. Okay. And so we'll have our bullet here, which will have some little m, and we'll be traveling at some velocity. Okay. Well, what happens is that it will hit this block, and it will embed itself in the block, and when it does, you have that this is then going to be free to swing, And now we're going to get that the bullet will be wedged inside here. So now this is going to be little m plus big M. And there will be this change in the height. Okay? And this system will move with some other velocity, v prime. Okay? So we're going to look what happens here in terms of this scenario. Well, again, there is going to be conservation of momentum. So you get the mass of little m, which in this case will be the mass of the projectile. So little m times v is going to equal little m plus big M times v prime. Right? So momentum before equals momentum after. We also had from earlier, we talked about in terms of kinetic energy and potential energy. And so you have that the kinetic energy and the potential energy just after collision is going to equal the kinetic energy and the potential energy at max height. Again, conservation of energy, we saw that in terms of the previous chapter when we talked about that object dropping. So in terms of what's going on here in terms of this, well, in terms of the kinetic energy, we get 1/2 little m plus big M times v prime squared. This will be 0 because it's at ground level, and this is my ground level when it's suspended. Okay? It's going to equal, at max height, we have that the kinetic energy has gone to 0, and then this will be the potential energy, which will be little m plus big M times Gh. So we have then 1/2 the mass v prime squared is going to equal m plus m Gh. Well, this term, m little m plus big M, appear on both sides of my equation, and so we end up with 1/2 the velocity after collision squared is going to equal Gh. I can give her the half by multiplying by 2, and so v prime is going to equal 2 Gh. And so v prime is going to equal the square root of 2 Gh. Well, then if we go back to what I had here, that the momentum before has to equal momentum after, well, then we could solve this for V. And so we have that V is going to equal little m plus big M over little m times G prime. And let's make this more of a big M, okay, which will be that. But then we know that V prime is given by this. And so the velocity of my projectile would be given by little m plus big M over little m times the square root of 2Gh. So we want to know in terms of a gun or whatever, how fast does it fire? We can basically fire it into this ballistic pendulum. And given that we know the masses of the block, the mass of the projectile, and we know how high up it went, we can then determine the velocity of our projectile. And in fact, that will be what you'll be doing in terms of the lab that deals with this stuff. So then, in terms of a question dealing with this formula we have here. So, what happens in this scenario? So we're going to use that equation, right, and we're going to solve this particular problem. So, we have that the mass of the bullet is equal to 3 grams. Right? The mass of the block is equal to 75 grams. And then the height, h, is 7.6 centimeters. Right? And I'm going to know what was the velocity of the projectile. So, my bullet is 3 grams, it's going this way, it hits the block, this whole system moves up by 7.6 centimeters, and now we want to determine the velocity of the projectile. First off, everything does need to be in the right units, so grams needs to be converted into kilograms. So this will be 0.003 kilograms. This will be 0.075 kilograms, and then this will be 0.076 meters. So first thing, make sure everything's in the right units. Now we can plug in. So the velocity will be 0.003 plus 0.075 divided by 0.003 square root of 2 times g, which is 9.8, times my height, 0.076. And we plug all that in, we find out that this projectile had a velocity of 31.7 meters per second. So another example of, in terms of an inelastic collision. Well, the last thing in the chapter deals with the idea of center of mass. And we'll see that when we get to some of the other chapters when we talk about center of mass in terms of torque and those sorts of things. And so, how do we find center of mass for a system? Right? So, center of mass. So, for example, we have a system, and so I have two objects. This one is 5 kilograms, located at the 1 meter mark. This one is 12 kilograms, located at the 5 meter mark. And so, if these two are connected by a rod that has no mass, what would be the center of mass for the system? One way you see center of mass come into play is if you think in terms of a mobile and how they are set up. Okay? Maybe they're set up based on using this whole idea of center of mass. Right? So then we got this ideal case where this rod that connects these two basically has no mass, okay? So it's not going to contribute anything. And I want to know, well, where's the center of mass going to be? Well, you probably know by looking at this, well, that the center of mass has to be closer to the heavier end of this thing. So X center of mass is given by M1, X1, M2, X2 over M1 plus M2. And so we can take our numbers, and we get that X center of mass is going to be 5 times 1 plus 12 times 5 over 5 plus 12. And that comes out to be 3.82. And so the center of mass is going to be down over here, which is what we said it had to be, because we knew it had to be closer to the heavier end in this system. And you know, this sort of thing could be taken out if you're talking about something in terms of an X or Y coordinate system. We could have in terms of Y center of mass, which would be M1 Y1, M2 Y2 over M1 plus M2. And then of course this could be expanded if I had 3, 4, 5, 6, 7 different things. And then if you were talking about an XYZ system, we could just add that next set in there in terms of Z's. Right? With that, that will conclude Chapter 7 on linear momentum.